Hello everyone. We'll wait for some more time before we start the session. Let's wait for others to join. All right, the last week's recorded videos could not have been uploaded uh, on YouTube yet due to some technical issues on our site. I'm sorry for that inconvenience. It will be uploaded along with the today's session on YouTube within a day or two. Meanwhile, while we are waiting for others to join the meeting, if you have any doubts regarding the previous week's lectures or the sessions or the practice problems that we have discussed, then you can ask them and we can discuss. I hope that my screen is visible and it is changing as well, the slides. If you can't see my screen, then please raise your hands or mention it in the chat box and I'll respond. Right. All right, let's start the session. Hello, everyone. Welcome to the fifth weekly discussion and doubt clearing session of the NPTEL course on concrete technology NOC24-CE46, which is taken by Professor B. Bhattacharya of IIT Delhi. I am Ashirvad Satpathy. I am a PMRF Research Scholar of IIT Delhi. What I do is I take these weekly sessions of 2 hours where we discuss the previous week's assignment problems, and we also take up the doubts that you might be having regarding the previous week's lectures. I'm one of the officially assigned teaching assistants to this course. I usually take my weekly sessions on Mondays from 6 to 8 p.m. There is another teaching assistant to this course. His name is Debojyoti. He usually takes his weekly sessions on Saturdays from 6 to 8 p.m. In today's session, we'll be discussing the week 4 assignment 4 problems. The week 4 lectures were regarding the supplementary cementitious materials or mineral additives that we use in cement and concrete, and how they affect the water demand, the superplasticizer demand, the porosity, and how they refine the pore structure of the cement and concrete when added to the matrix. These were the issues that were discussed in these week 4 lectures. And at the end of the session, we'll also be taking some of the doubts that you might be having regarding the week 4 lectures. So the first question of this assignment was, which of the following is not a pozzolanic material? Fly ash, silt, silica fume, ground granulated blast furnace slag, or GGBFS. Which of these four options is not a pozzolanic material? Can somebody answer to this question? Please raise your hands to answer so that I'll allow your microphones. Which of these materials is not pozzolanic in nature? Fly ash, silt, silica fume, GGBFS. Yes, Tobias, Suvitha, Deepika. What is a pozzolanic material? Can somebody answer to this question first? What is pozzolanic material, or what is a pozzolan, or what is a pozzolanic reaction? Okay, I see that Divya has also joined. The question is, which of the following is not a pozzolanic material? Fly ash, silt, silica fume, GGBFS. All right. The correct answer to this question is silt. Silt is not a pozzolanic material. Fly ash is, silica fume is, and GGPF is. All these three are pozzolanic materials, but silt is not a pozzolanic material. And what is a pozzolanic material? To answer that question, we need to understand how the pozzolanic, what reaction does make a material pozzolanic in nature. So normally, this is a um, reaction diagram or the flow chart that I have taken from the internet, and this is to show you how cement reacts with water and what are the ions involved in the process. So cement, or mainly the constituents of cement, let's say A-lite and B-lite, the major two constituents of cement, they react with water, and the first reaction that undergoes is the dissolution. So the dissolution of the cementitious phases. And in this first phase, the cement phases dissolve and release calcium ions, and the silica from these phases also dissolves in the water and forms this silicate ion. And then there is OH minus ion coming from the water, right? Now, the calcium and the silica react together and along with water to form the CSH, which is called the calcium silicate hydrate. You've also seen this in the lectures, right? And this silicate hydration product is responsible for most of the hardened strength that we get from in the concrete, right? Yeah, along with the production of CSH, or calcium silicate hydrate, um, uh, in this reaction, there is another byproduct that we get in this reaction that is known as portlandite or calcium hydroxide, right? Now, when you add something such as a fly ash, silica fume, or GGBFS to the cement or concrete, what these three type of materials, or most of the pozzolanic materials or cementitious materials have in common is reactive silica or reactive alumina. Reactive silica and reactive alumina. And the reactive silica and alumina coming from these pozzolanic materials dissolves in water and reacts with the portlandite or the calcium hydroxide that is produced from the cement hydration reaction in order to give us additional CSH or additional calcium silicate hydrate. So this is the pozzolanic reaction part, in which the reactive, this is the reactive silica, reactive in nature. So reactive silica dissolves in water and it reacts with the calcium hydroxide coming from the cement hydration. So this is the cement hydration reaction. In order to produce the additional CSH that we get from this pozzolanic reaction. So basically, what is a pozzolanic material? It is a material that has reactive silica and requires lime to get activated, and lime and water to react with and produce calcium silicate hydrates. So this is what a pozzolanic material is. Fly ash, silica fume, and GGBFS, all of these materials have amorphous and reactive silica, while silt is, even though silt has silica in it, but that is majorly crystalline in the form of quartz. So, as we have also seen in the previous sessions, crystalline materials are not very reactive. They are stable materials. They're not very reactive in nature, and so this crystalline silica is present in the form of quartz, and therefore silt is not a pozzolanic material, right? Moving on to the second question, the purpose of adding pozzolanic material in cement is, and the options given are to reduce water demand, to increase workability of cement paste, to act as a supplementary cementitious material, none of the above. Which of these options is correct with respect to adding pozzolanic materials in cement? Yes? Can anyone try? What is the major purpose of adding pozzolanic materials in cement? It reduces the water demand or increases the workability. or it acts as a supplementary cementitious material, or none of these. All right, that is pretty straightforward. We've already discussed it. It is to act as a supplementary cementitious material. This is the correct answer. So basically, pozzolanic materials are also called as supplementary cementitious materials, meaning that they supplement the cementitious reactions. They produce additional hydration products which contribute to the strength and durability of this cementitious of the cement and concrete. So this is the correct answer. They don't reduce the water demand. In fact, they sometimes increase the water demand due to their high surface area and very finer nature of the particles, finer size of the particles. They also do not increase the workability of cement paste. I mean, they could so provide somewhat of a plasticizing action in case of spherical particles, but they by and large they don't increase the workability of cement paste, so that is not the correct answer. So the correct answer is they increase the supplementary cement. They act as a supplementary cementitious material, right? The third question is, what is the effect of mineral admixtures on the initial and final setting time of cement? It increases significantly the setting time. It decreases significantly. No adverse or significant effect is observed. Which of these is observed with respect to addition of mineral admixtures on the setting time of cement? The setting time increases, it decreases, or it is not affected much. Which of these is the correct answer? Yes, this is actually a tricky and interesting question as to how you want to answer this question. Yes, can somebody try answering this question? What is the effect of mineral admixtures on the setting time of cement? Do they increase the setting time? Do they decrease it? Or they do not have much of a significant effect on the setting time of cement? Divya, Savita, Tobias, anybody wants to try? I I urge you to engage in this session, engage in discussion so that we all learn from these sessions. If you have any doubts, you can ask them. If you have any insights on these topics, then we are happy to hear you. Let's make this interactive. For a start, I will allow all of your microphones so that you don't have to raise the hands because there are not a lot of participants in the session anyway. Yeah, I've allowed all of your microphones so you can just unmute yourselves and speak. How do the mineral admixtures affect the setting time of cement? Does anybody wants to try? Okay. So the correct answer that is given in the I mean in the assignments is it has no adverse or significant effect. So basically what it means to say is that mineral admixtures directly do not affect the setting time anyway, because mineral admixtures have undergo a slow reaction. They first undergo a slow reaction, and second, they need sufficient Portlandite in order to react. So mineral additives themselves do not control the reaction kinetics directly, because they undergo a slow reaction. So their contribution to the reaction, the hydration products, and thereby the strength and durability comes at a very later stage, at ages beyond 28 days or so, in case of at least fly ash. And again, they need sufficient CH or Portlandite coming from the cementitious reaction in order to react themselves. So if there is no Portlandite in the system, in the cementitious matrix, then these mineral admixtures are as good as inert fillers. They do not contribute anything towards the hydration products. They do not provide any additional hydration products in the cementitious matrix. So these are the two main parameters that control the late reactivity and late contribution to the strength and durability of these mineral additives. But there is one or more ways in which these mineral additives can indirectly affect the setting time of cement. How? Let us say, and we know that these mineral additives have a size, so finer size distribution, and many of these mineral additives have high specific surface area, right? Like you have seen in the case of um, silica fume or rice husk ash, these mineral additives have very high specific surface area. Now, what happens is when you add these finer and materials with very high specific surface area to the cement, they act as fillers, and they produce what is known as the nucleation effect. What is the nucleation effect? Essentially, these are sites, these mineral additives act as sites for the nucleation of hydration products. So, meaning that nucleation is basically uh, a spontaneous expansion, not expansion exactly, growth, growth of materials forming links with one another. So basically, these materials, these finer materials with very high surface area, they act as sites for the deposition of um, these hydration products, and thereby the formation of these links leading to the nucleation. And when this nucleation effect comes into place, so this is the site, and these are the hydration products getting nucleated over them. Right? And when this nucleation product comes into play, that increases the heat of hydration of the overall cement or overall cementitious matrix, including the SEM as well. And when this hit of hydration increases, we know that the setting time is also affected, meaning that the setting time decreases. So due to this nucleation effect also, the setting time could vary a little bit, but this is not the direct influence of the mineral admixtures on the setting time. Rather, they act as just sites to provide for the nucleation of these hydration products, and in order to increase the reactivity of clinker. So they don't themselves react, rather they increase the reactivity of clinker due to the presence of these large surface area sites. So this might reduce the setting time somehow. Now again, how it might so happen that when you add the mineral admixtures in huge quantities, they might increase the setting times as well. How so? Because if you replace a major chunk of the cement with these mineral admixtures, then the reactivity of this, as we know that the mineral admixtures have a low reactivity, and there won't be enough cement in the system itself for the whole system to set. So in a way, what we are doing is we are uh, keeping the reactive material in a low quantity, so it is not enough for the whole for it to make the whole system into a hardened one. And again, the materials that are in huge quantity, that is the mineral admixtures, they have a low reactivity, so they are going to set at a later age. So that, if you that might happen if you add these mineral admixtures in huge quantities. If you replace the cement with mineral admixtures in huge quantities, they can, in a way, increase the setting time. So again, this is an indirect effect. They don't directly affect the setting time anyway. So indirectly, if added huge. So this is what is the summary of how the mineral admixtures have an effect on the setting time of cement, right? Moving on to the fourth question, which of the following process produces fly ash as a byproduct? Burning of coal in thermal power plant, metal production in blast furnace, silicon and ferrosilicon production, none of the above. Which of these industrial processes leads to the production of fly ash as a byproduct? Yes, does anybody want to try?
Hello, sir.
Yes,
Am I audible?
yes, Tobias, you're audible.
Okay, I think option number one is the
Okay,
correct answer of coal in thermal plant
right.
because they use the which are contaminated by clay.
Pardon, what do they use? Okay. All right. Thank you, Tobias. Yes, the burning of coal in thermal power plants leads to the formation of fly ash as a byproduct. Metal production in blast furnace. So basically, in the case of iron production, it is blast furnace slag. It leads to blast furnace slag, as the name itself suggests. So slag is basically clay materials that are present in the iron ores, and uh, lime is introduced in while the production of iron. Lime is mixed up with these iron ores, and when it is heated up, these the clay material from the iron ore combines with the lime and floats over the metal, over the molten metal, and that is collected as slag, while the molten metal is flown out from the bottom. So that is the blast furnace slag. and it is ground and and comes in granulated form, so it is called as GGBFS. Silicon and ferrosilicon production leads to silica fume production. So again, silica, very high purity silica is used in these cases, and um, when this it is fired at a very high temperature in the kiln or the furnace, these there are the gaseous fumes are released from the furnace, and they also contain very fine amorphous silica particles along with the gases. Now it passes through a electrostatic precipitator, and it is condensed down, and that's how silica fume is separated out from these gaseous materials, and after that the gases are released into the atmosphere. So this silica fume is collected from these silicon and ferrosilicon production. And finally, when burning coal in a thermal power plant, what we do is we burn the coal at very high temperatures in order to increase the temperature and convert the water into steam, which in turn flows on the steam turbines and produces electricity. So when this coal is burned at high temperatures, it turns into ash, and the ash that is collected in these in the gaseous fumes coming from the furnace, that is again passed through electrostatic precipitator, and that leads to the formation of fly ash, while the ash that is collected at the bottom of the blast furnace, that is known as bottom ash. I guess I have a okay. I have this picture on the next slide, and this is a typical schematic representation of how fly ash is generated in a power plant. So this is the point where you feed the coal in the coal silos. This is the coal being fed over here, and then it is pulverized. Pulverizes size reduction. Pulverization is size reduction, and then it goes into the boiler. So the coal is being fired inside this furnace, and in the boiler there is water coming from outside into the boiler, and due to the firing of the coal, this water gets converted into steam, and this steam goes to the turbines, and in turn the turbines generate electricity through generators, and that is transmitted to the transmission lines. On the other hand, the gaseous fumes that are generated in this furnace, that go into these electrostatic precipitators, and these precipitators precipitate out the fly ash from these fumes, and finally the fumes are released into the chimney. So this fly ash, this is a dry process. The fly ash can be stored in directly in silos. There is a wet process also, wherein the fly ash is mixed up with water and stored in storage in ponds. So that is wet process. And the bottom ash that is collected in these the bottom portion of the furnace, that is also used as bottom ash, right? So yeah, this is the typical process of fly ash production in thermal power plant. Moving on to the fifth question, which of the following mineral admixture results in increase in water demand? Fly ash, GGBFS, silica fume, rice husk ash. You could say in terms that which among of these has the highest water demand and why? I mean, most of these mineral admixtures increase water demand when added to cement or concrete. But which of these mineral admixtures, fly ash, GGBFS, silica fume, or rice husk ash, which of these has the highest water demand and why? Yes, can somebody try answering this question? Anybody? Which of these admixtures has mineral additives have uh, the highest water demand? Fly ash, GGBFS, silica fume, rice husk ash. Yes, does anybody want to try? All right, the correct answer to this question is rice husk ash. It has also been discussed in the lecture as well. So I have comparison of the specific surface area uh, estimated by the BET method of all these mineral admixtures. And for fly ash, the BET SSA comes around one ranges around 1 to 3 meters square per gram. For GGBFS, it is again around 0.5 to 4, depending on how fine you want to grind it, and so basically that also affects the grinding also affects the specific surface area a little bit of in case of slag. In case of fly ash and silica fume, they are already in a fine form because they have a spherical shape as they have been precipitated out from the fumes. So they come in a spherical shape and they are already in a very fine state. So they have so fly ash has a specific surface area around 1 to 3 meters square per gram. Slag has around zero point 0.5 to 4 meters square per gram. Silica fume has a higher specific surface area and even a lower particle size among all these as well. And that ranges around 15 to 25 meters square per gram. Whereas rice husk ash can have a specific surface area ranging from 20 meters square per gram till 270 meters square per gram. And this is influenced by the morphology of the rice husk ash particles, as you can see on this view graph. These rice husk ash are made uh, out of a cellulose microstructure, cellulose based microstructure, and therefore they have this microporous structure that leads to a enlarged specific surface area as shown over here. So you have these fibrous and porous microstructure in case of rice husk ash particles, and due to that they have a very high specific surface area. And you know that when a material has a very high specific surface area, it will increase the water demand because it will absorb significant amount of water that is present in the total pore solution or the mixing water that you are adding to concrete, and thereby it will increase the water demand for the same workability or the same flowability that you want in your cement or concrete. So rice husk ash, due to its fibrous cellulosic microporous structure, it has a high SSA, high water demand, right? So rice husk ash is the correct answer. Coming to the sixth question, which of the following mineral admixture requires the highest dosage of superplasticizer and why? Fly ash, GGBFS, silica fume, rice husk ash. Which of these type of admixtures, mineral admixtures, requires the highest dosage of superplasticizer? Yes, Tobias?
Hello, sir. Okay, I think it's still the rice husk ash
It is rice husk
because
ash.
of the
Mhm.
yes, because of the larger specific surface area.
Okay. Okay.
Yes.
All right. Because of the high specific surface area. All right. Thank you. Anybody else wants to try? Anybody else wants to try answering this question? Yes, the correct answer is rice husk ash, as Tobias has already rightly mentioned, and it is due to the same reason that we have already discussed. It has a fibrous microstructure, and if you see in this um, scanning electron micrograph, so when superplasticizer is added to a system, superplasticizer, uh, this is the answer, yeah. When superplasticizer is added to a system, it essentially disperses by two actions. One is adsorption, and the other one is intercalation. Adsorption is good for us because so when superplasticizer comes onto a particle and it adsorbs, gets adsorbed on the surface. So this is a superplasticizer molecule. It adsorbs on the surface. These are the graph chains, let's say. Therefore, it pushes the other particles further apart. And this pushing apart increases the dispersion in the system. So adsorption increases the dispersion. So it is good for us. It is the desired use of superplasticizer, that it adsorbs onto the solid particles and disperses them further apart in order to produce a plasticized system. But there is another effect that goes on when we add superplasticizer to the system, that is intercalation. Intercalation is what? Let us say we have certain layers of these particles. A solid particles has a layered structure, and these layered network of of the sheets causes the superplasticizer to get trapped in between these layered network, right? So the superplasticizer molecules get trapped in between the layered network, and that is intercalation. And due to intercalation, there is less superplasticizer available for adsorption because some of the superplasticizer is consumed due to intercalation. And this intercalation is happening at a structural level. At For a single solid, let us assume a single solid as shown in this figure as well. This single solid, this is where in between these layered fibrous structures, microstructure, the superplasticizer molecules get trapped, and therefore they're not available on the surface to get adsorbed in order to push apart the particles, right? So intercalation reduces the amount of superplasticizer, less superplasticizer available for adsorption, and in turn dispersion. So when there is less superplasticizer available for adsorption, that will increase the superplasticizer demand of the system. And therefore, due to this fibrous and microporous network of rice husk ash, it intercalates a lot of superplasticizer molecules that are being added into the system, and therefore less amount of superplasticizer is available for adsorption and dispersion, and that in turn increases the demand of the superplasticizer. Moving on to the seventh question, which of the following uh, exhibit pore filling effect in cement? Is it fly ash, GGBFS, silica fume, rice husk ash? Which of these admixtures, mineral admixtures, exhibit a pore filling effect in cement, and why? Yes, can somebody answer this question? Which of these, I mean, all of the mineral admixtures exhibit a pore filling effect to some extent, but you can answer in terms that which of these mineral admixtures has the highest pore filling or pore refinement capacity among the four listed. Which of these has the highest pore filling or pore refinement capacity, and why so? Can somebody try and answer this question? I've allowed you microphone, so you just have to unmute yourself and speak. Yes, Sagar, you want to say something?
Yes, sir. Fly ash, sir.
Fly ash, okay. Why so?
Sir, fly ash is very fine particles.
Okay. Which of these? So, what do you say that? Do you say that pore filling is done due to fineness of the particles?
Yes, sir.
Okay. Then, which of these mineral admixtures has the I mean, finest particles? Which of these mineral admixtures has the finest particles, or in maximum fraction of the particles in a finer range?
Yes, sir.
Which of these do you want to say? Does fly ash have the finest particles among the four?
Yes, sir.
Okay. All right. Thank you, Sagar. Does anybody want to try? I have also discussed this in one of the previous questions already, so it is going to be easier anyway. Which of these has the highest pore filling capacity? All right. Okay. Sagar actually rightly mentioned that pore filling capacity is characterized by the fineness of the particles in a given material, and therefore the highest pore filling ability comes from silica fume. So the correct answer to this question is silica fume and not fly ash, because silica fume has the finest particles. All right. Among all the four mentioned over here, silica fume has the finest particles, and I have taken a view graph from one of the research papers, and you can see that this is the pore volume intruded calculated from MIP, mercury intrusion porosity, porosimetry, and this is the percentage of um, silica fume addition, this being 0, 4, 8, 12, 16, and 20. And you can see that upon increasing addition of silica fume, the total porosity decreases, as well as the pores also become finer, meaning that um, uh, if you if you see at a given stage between 10 nanometer and 100 nanometer pore size, at 0% addition of silica fume, a higher volume of this pore size is available. However, at 20% addition of silica fume, the pore volume is reduced at this given radius of pore size. All right. So with increasing addition of the silica fume, the total porosity decreases, pore size decreases. the pore size also gets decreased, and this is also known as pore size refinement. So the larger pores, when there is no silica fume added in the system, the pores were larger in size. Now, when you add a finer material, which are which have particles so fine that they are also in have a comparable size as that of the pores present in the cementitious matrix. So these finer particles clog these pores and reduce the larger size of the pores into smaller size pores. So that is what is called as pore size refinement or pore structure refinement. And this happens in maximum degree in case of silica fume, because silica fume has the finest particles among all these four materials. Fly ash also has fine particles, but fly ash and GGBFS are known to have particles around the same or a little bit of lesser size than that of the cement particles itself. But silica fume has very finer particles, and therefore silica fume also requires a special dispersion before being added, dispersion required before added to concrete. So silica fume cannot be directly added as a powder into the concrete mix. It has to be prepared in a slurry form, because silica fume particles are so fine, they're in a very flocculated state, and therefore they have to be dispersed first in a slurry form using sonication and ultrasonication methods in order to disperse these particles, and then only you can use it in concrete. And due to this fine particle sizes, they refine the pore structure, right? Moving on to the eighth question, which of the following is a point of concern and should be taken care of while using silica fume as a mineral admixture? Is it strength? Is it creep? Is it shrinkage? Or none of the above? Which of these is a point of concern when we are using silica fume as a mineral admixture in concrete or cement? And why?
Sir, it's strength, sir. Strength.
Is it strength?
Strength, sir.
Okay. Okay, thank you, Sagar. Does anybody else want to try? Why do you say that it is strength?
Sir,
That means
because strength, when silica fume is added in cement, the combination of generation is very bonding to gypsum and very fine particles. It's so increases its strength.
it increases the strength, right?
Yes, sir.
Yeah, so that is not a point of concern then. So by point of concern, it means that what is affected,
Affected.
disadvantage. Yeah, you have to find the disadvantage of adding large amount of silica fume. What is the disadvantage? So strength is increased when you add silica fume to concrete or cement. So that is not a point of concern then. Which of the other parameters is a point of concern, and why?
Yeah.
Okay, let's forget the why part. Which of the parameters is a point of concern?
Point of disadvantage.
Yeah, it's a disadvantage of adding high amount of silica fume in concrete.
Sir, it's creep or shrinkage between.
Of course,
I
it is
think
going to be creep or shrinkage because we have already ruled out strength. That is not how
okay.
you have to pick one, and why. You have to mention why.
Shrinkage, sir. Sir, it's
Shrinkage.
shrinkage.
Okay. Okay, thank you. But how? How? Okay, admit it. But how do you say that addition of high volume of silica fume in concrete increases the shrinkage? You mean to say that the disadvantage is that it shrinkage gets increased, right?
Yes.
Yeah. How does it increase the shrinkage?
Shrinkage. सर मिनरल एडमिक्सचर है तो
So,
डिपेंड it's not adding to
what causes shrinkage? Let us first discuss what causes shrinkage in case of in cement. What is the cause of shrinkage? Shrinkage कैसे होता है सीमेंट में? फर्स्ट ऑफ ऑल श्रिंकेज में होता क्या है ये बताओ. Yes, anybody? What is shrinkage in cement or concrete? We've already discussed this in one of the previous sessions, so you should be able to answer this. And we have it has been taught very well in the lectures as well. So, and this is very basic. What is shrinkage? I'm not asking about how shrinkage occurs or what causes shrinkage in cement or concrete. I'm just asking what is shrinkage. Yes, Sagar or anyone else? Tobias, Suvita, Divya Srijiki. You've been silent throughout the session. Do you want to answer something? Pavitra? Okay, well, now we have Deepika as well. Deepika, we just to highlight, we are discussing what is the point of concern, meaning that what is the disadvantage of adding high volume of silica fume as a mineral admixture? Is it strength? Is it creep? Is it shrinkage? Or is it none of the above? And why so? So already Sagar has highlighted that when we add high volumes of silica fume, it results in high shrinkage. And then I want to ask the question that why does high volume of silica fume cause shrinkage? And before going to that area, I'm just asking what is shrinkage? What is shrinkage in cement or concrete? Shrinkage is the reduction of volume, right? Right. So the correct answer is yes, it is shrinkage. I'll just mention what is shrinkage. Reduction of volume. Now, how does the volume get reduced? How does the volume get reduced by shrinkage? By expulsion of water from the capillary pores. We have already discussed this in the different types of shrinkage in one of the previous sessions, be it plastic shrinkage or drying shrinkage or autogenous shrinkage or chemical shrinkage. Whatever be it, it is characterized by reduction in volume, and this reduction in volume is caused due to the expulsion of water from the capillary pores of the cement or concrete, right? Now, in case of chemical or autogenous shrinkage, this capillary water gets expelled from the pores and goes on to react with the cementitious products. In case of drying shrinkage, this capillary water is sucked out of the pores and dries up into the atmosphere. So that causes the shrinkage. Or in case of in case of plastic shrinkage also, it rises up to the surface and there is a subsidence of the total volume, and this water gets evaporated into the atmosphere. So shrinkage is basically reduction in volume caused by the expulsion of water from the capillary pores. Now, when there is expulsion of water from the capillary pores, and by I need you to focus on this word, the capillary action induces capillary tension, right? When the water moves through these capillary pores, in or out, that in, increases the capillary tension. So when the water moves out, that creates capillary tension and that causes the shrinkage. If the shrinkage is restrained, meaning that if it is occurring in a hardened state or after the concrete has set, then this tension will cause cracks inside the concrete, right? Now, when you have no silica fume in the cementitious matrix, so I'll discuss this first. When no silica fume is present in the matrix, the pore size are large. Let us say these are the concrete particles and this is the pore size, right? So it has a large pore size. And when the pore size is large, the surface tension is less. Surface tension or tense force in the capillary is less. But when silica fume is added, now what happens? Let us say these are the cement grains and this is the pores. And now the silica fume is also combined, constituting some of the volume of the pore size. So now the pore size is small, right? Pore size is now small because silica fume has already reduced the pore sizes. And due to the small pore sizes, the surface tension force in the capillary is increased, right? And when the the tensile force in the capillary is increased, now the with the previous in the previous case it was a lesser force, so only less amount of water was going to expelled due to the shrinkage. But now since the force is higher, it is going to expel more water from the capillary pores. So that way there will be higher amount of shrinkage, there will be higher amount of volume reduction. So when you use these finer materials, very fine materials such as silica fume, they clog these large pores and decrease the size of the pores. And due to the decreased size of the pores, the surface tension forces in the capillaries rise, they increase in degree, and therefore that induces higher shrinkage amount in the cementitious matrix. So this is the whole mechanism of how shrinkage occurs in cement and concrete, and how these fine supplementary cementitious materials can induce higher shrinkage in the cementitious matrix. All right. And in order to explain how silica fume influences the shrinkage in cement and concrete, I've taken these two pictures from two research papers, and you can see that in the first view graph, this is the plain concrete without any silica fume. This is 5% silica fume. This is 7.5% silica fume. And finally, this is 10% silica fume. And this is the plastic shrinkage strain in micrometer. So not plastic shrinkage in micrometer, and it's a linear deformation that you're measuring, and we are and this is the time in hours from the addition of water. And you can see that with the increase in amount of silica fume, the plastic shrinkage increases, right? And when you consider autogenous shrinkage, as you can see, if let me check if I can zoom it. All right, yeah. So this is the autogenous shrinkage, and you can see that when you this is 0% silica fume, that is 5% silica fume, and this is 10% silica fume, and this is at water to cement binder ratio of 0.26. And this in the x-axis you can see that the varying age of the specimens, and you can see that with increasing amount of introduction or replacement with silica fume, the autogenous shrinkage increases, and this is invariably so in all the water to cement ratios. This is at water to binder ratio of 0.3, and you can see again the highest autogenous shrinkage is occurring in case of 10% silica fume, and finally in at water to binder ratio of 0.35, you can see that still uh, the highest autogenous shrinkage is coming for 10% silica fume. And you can also notice one fact at water to binder ratio of 0.35, The concrete or the cementitious specimen with no silica fume has almost a constant autogenous shrinkage. I mean, the autogenous shrinkage has stagnated after around 14 days or so, whereas in the case of the specimens with silica fume added to them, the autogenous shrinkage continues to occur even after till 100 days. So this is how silica fume, sorry, which one were you talking about? Yeah. So this is how silica fume contributes to the shrinkage, different types of shrinkages in cementitious matrix, right? Moving on to the ninth question, which of the following mineral admixture results in lowest water demand? We have already talked about the highest water demand. Which of these mineral additives has the lowest water demand and why?
Sir, I have to one question.
Yes, Sagar, go ahead.
Sir, how much replacement of silica fume maximum limit as per IS code, sir?
As per IS code, I'm
Yes,
not
sir.
sure. I don't have the values in my head right now, but it depends on. We don't use silica fume directly as a replacement in cement. Like
Uh,
in order to produce blended cement, we use slag to
uh,
produce composite cement. We use fly ash to produce pozzolana cement, but we don't use
okay.
silica fume directly to produce cement. But we can use silica fume in concrete.
Okay.
And in order to produce high strength concretes of, let us
Uh,
say, 100 or 200 megapascals or so, it is
okay.
essential to use silica fume because without silica fume, you won't be having such finer materials in your mix, and
Okay.
therefore you won't be having reduced pore size and pore volume, and therefore you
Hmm.
won't achieve such high strength. So you need to introduce silica fume to the concretes. But generally, these in the case of these high strength and high performance concretes, the silica fume ranges around 5 to 10% or maximum of 15%, but not beyond that. So
Okay, sir.
yeah,
Thank you,
so
sir.
it ranges around 5 to 15% because beyond that it increases the issues of water high, I mean workability loss and all of that issues. The fresh properties are affected quite highly, and again, as we mentioned, there is issues of shrinkage, creep, and so on. So we tend to keep the amount of silica fume within that range.
Okay, sir. Thank you.
Okay, all right.
Thank you, sir.
Yes. Anybody wants to answer this question? Which of the following mineral admixture results in lowest water demand? Fly ash, silica fume, rice husk ash, all have equal water demand. Which of these options is correct?
Sir, rice husk ash.
It is talking about lowest water demand. You also mentioned, we also discussed that highest water demand is coming from rice husk ash. I'm asking about the
Sorry, sir.
lowest water demand.
Yes,
Or do all of them have equal water demand?
yes, sir. I think all have equal water
No,
demand
we have
previously.
already discussed that rice husk ash has the highest water demand. So this is not the right answer. So which one of these has the lowest water demand? So the correct answer to
Lowest
this
water.
question is fly ash actually, and it has been already discussed in the NPTEL lecture as well. Fly
Okay.
ash has a kind of a plasticizing action due to the morphology of the particles of fly ash. So fly ash has a spherical particles morphology.
Okay.
The particle size are comparable to that of cement, and therefore the specific surface area is low because both fly ash and silica fume have spherical particles. Fly ash has a spherical particle and silica fume have a spherical particle, but silica fume has very less particle size, as we discussed, less particle size, and hence high SSA in case of silica fume. But in case of fly ash, as you can see on this view graph, this is the mean size in micrometers, and it ranges around 10 to 15, which is also similar to that of cement. Similarly, for rice husk ash, it is around 10 to 20. Ground GGBFS, it is not mentioned because you can grind GGBFS. It comes in a granulated form, and you need to grind it to the fineness that you want in. While these ashes or silica fumes, they come directly in a very fine state. And metacolin also is very finer, whereas silica fume is the finest among all these mentioned supplementary cementitious materials. When you talk about specific surface area, you see that fly ash has a low specific surface area ranging from around 1 to 3. Rice husk ash has the highest specific surface area, as we already discussed. Again, GGBFS has the same specific surface area around that of fly ash. Silica fume again has a high specific surface area, and this is due to the low particle size. Because lower the particle size, higher is going to be the specific surface area, at least in the case of spherical particles, right? So yeah, so the particle shape in fly ash is spherical, GGBFS is irregular, rice husk ash is cellular, as we also saw in the scanning electron micrograph. Again, silica fume has spherical particles, and metacolin has platy or sheet-like structures. So fly ash has the lowest water demand due to its spherical particle shape, and this spherical particle shape also contribute to what we call as the ball bearing effect. Ball bearing effect, plasticizing action coming from the fly ash. So sometimes using fly ash can in fact increase the workability to a certain extent, or if not increase, at least it won't decrease the workability if you add fly ash to a limit. And this happens due to its spherical particles, which cause the ball bearing effect, and it has a particle size comparable to that of cementitious cement grains also, and therefore it has a low specific surface area, right? So therefore fly ash among all these supplementary cementitious materials has a low water demand. And this brings us to the final question of this assignment: which of the following code or standard is the Indian standard for test of pozzolanic material, the reactivity of pozzolanic materials? Is it IS 1383, 1293, 1787, 1727? Does anybody know the answer to this question? All right, this is a no-brainer. The correct answer to this question is it is IS 1727, 1967, which was also reaffirmed in the year of 2018. This is the uh, Indian standard for testing the reactivity of pozzolanic material, right? So this is the Indian standard. So this basically is lime reactivity test. We call it as. In other words, it's the lime reactivity test, right? So that ends the discussion of the assignment problems of week 4. If you have any questions, then we can discuss them. If you have any doubts regarding the lectures or regarding these sessions, then we can discuss them. The session will go until 8 p.m. And if you don't have any doubts or questions, then you can leave the session. Otherwise, if you have any doubts, you can stay up and we can discuss, right?
Sir, can we use uh, PPC cement for concrete?
Yes, Sagar,
Hello.
we do use PPC for concrete, in fact. PPC is a standardized cement in India, Portland Pozzolana
Yes.
cement. It uses fly ash, and we do use it to make concrete. It is already in the market.
Sir, but many plants using only OPC cement, ordinary Portland cement, 53 grade.
Okay, that could be the client's or the project owner's requirement, but if there is no such requirement, then you can go for any of the cements, standardized cements that are available commercially. But if the client or the project proponent requires a certain kind of structures to be made with a certain kind of a cement, then yeah. But anyway, with the, I mean, recent emphasis going towards low carbon cements and lowering the carbon footprint of the construction industry and the cement industry, it is going, the ordinary Portland cement is going to be obsolete in some in a few years. So we will
But
have to move towards low carbon cements like Portland pozzolana cement or composite cement using slag, or the recently introduced limestone calcine clay cement. Yeah.
okay, sir.
I mean, already a lot of the companies have stopped producing ordinary Portland cement for commercial purposes. They only provide it for research purposes. But other than that, in India, it is going to occur in a few years. I mean, the consumption of ordinary Portland cement for projects will be reduced to almost nil. It in Europe and other sections of the world, it has already started, and companies have already stopped producing commercial ordinary Portland cement for projects, for infrastructure projects. Yeah. So we'll have to move towards these options. So whatever the locally available material that you have, let's say you have fly ash, so you make pozzolana cement, or you have slag, or you go for a slag and fly ash, you go for a composite cement. Yeah. But it is totally safe to use any kind of cement that is prescribed by the Bureau of Indian Standards.
Okay, sir.
Anyone else have any questions, or doubts, or queries? How many of you have registered for the exam of this course, the certification exam?
Sir, I am also.
You applied for it? Okay. All right.
Hello, sir.
Yes.
How to control concrete temperature in summer season, sir? Normal.
Okay. So basically, if you're concreting at very high temperatures or in regions where the summer temperatures go beyond 40 to 50 degrees Celsius, that becomes a problem because um, till 40 till 30 degrees Celsius or so, till 30, 35, 40 degrees Celsius, it is all right. We will be able to it won't affect the reaction so much. But beyond 40 and beyond 50 degrees Celsius, it is going to affect the reactions. And then what we would do usually is we use cold water for concreting. So when you use cold water, the heat that is getting released from, let's say, how the way we do it for mass concreting as well. So we use cold water for concreting, and thereby the materials are already hot, the raw materials, meaning that the aggregates, the cement and everything is hot due to the temperature, and the weather is also hot, so the temperature outside is increased, and due to the cementitious reactions that are going inside um, the the concrete, that is also releasing heat and thereby increasing the temperature. But when you use cold water, this heat is getting compensated by the cold water, and therefore it maintains the temperature inside the concrete to normal levels. So that way you can control the temperature of uh, these concrete structures in summers. So the one way is to go with cold water.
When concrete lose its plasticity, how
Mhm.
many uh, redosage again and again? How many times?
There is no such. So by redosing, you mean what is the redosing number for super plasticizer, right?
Yes, sir. Super plasticizer or plasticizer or retarder or
Okay.
accelerator.
First of all, it is not recommended
Okay.
to redose admixture in concrete, because when you carry out a concreting and you're adding super plasticizer to your concrete, you essentially what you do is you correct the water
Yes.
for the water content of the super plasticizer. Do you do that? Are you a engineer in somewhere in a company or so?
Yes, sir.
I mean, do you have any site experience?
Yes, sir. I have to side it, please.
Okay, so all right, just asking. I just wanted to know. So yeah, when you do concreting, you when you add super plasticizer to concrete in a concrete mixture design, you must be
Yes, sir.
correcting your water for the super plasticizer that you have added, right? Now,
Yes, sir.
yeah. So you essentially what you do is the amount of super plasticizer, the amount of water that is present in the super plasticizer, that is deducted from the mixing water that you're adding, right? But
Yes, sir.
when you once you have added that super plasticizer and you have already prepared the mix, now you want to redose the super plasticizer, and the amount of super plasticizer that you are using for redosing, you are not correcting the water for that. So first of
Yes,
all,
sir.
so that is not the right way to do it, because essentially what you're doing is you're increasing the water to cement ratio by a little bit in your concrete mix. Again, that won't affect the concrete mixture a
Quality
very
on concrete.
in a very large way, because the water to cement ratio is increased by a very small fraction, but it is not the right way to do it first of all. Secondly, redosing depends on, I mean, if you want to discuss it anyway, then redosing depends on a lot of factors. The amount of the workability that you want in your mix, meaning that the open time that you want in your mix, and open time is the time between the water that you add and till you pour it into a structure. So let's say you want an open time of 2 hours, and depending on that, you need to carry out some trials in order to figure out the amount and the time of redosing of your super plasticizer. And the second thing is, if you want a retention in your concrete,
Okay.
so the retention time that you want in your concrete, based on that, you'll be able to figure out the amount and the time of the redosing. Sometimes it happens so that when you add all of the superplasticizer at once, the concrete might segregate a bit. So in that cases, it is admissible to use the redosing method, or the delayed dosing method that we call it. So meaning that not all of the super plasticizer is added at once in the mixing water. Some of the mixing water is first added to the concrete without the super plasticizer. It is rested for some time, and then the super plasticizer and the rest of the mixing water is added to the concrete. So that is a delayed dosing method. In that is done to reduce the segregation in the mix, because with especially in the case of self-compacting concrete mixes, what happens is when they require a high amount of super plasticizer in the mix, and due to this high amount of super plasticizer, segregation and
Like, sir,
bleeding is observed.
very sticky that time.
Yeah,
Very sticky.
yeah, it is
So,
sticky,
fully
and
stagnant.
yeah, due to the high amounts of super plasticizer, sometimes there is segregation and bleeding in the mix. In order to avoid that segregation before pouring, what we do is the delayed dosing. That means that you add the super plasticizer at a little bit, let's say 15-20 minutes after you have added some of the water. in the concrete, and you have allowed for the reactions to occur. Now, once the reactions start to occur, the water demand will increase, and then when you add the superplasticizer, it won't segregate much. So there, that will ensure both the things. It will ensure you have a higher retention time because you're adding superplasticizer at a later stage, and it will also ensure that you obtain a stable mix without any effects of segregation and bleeding, and you achieve your uh, desired workability or the slump that you're targeting. But redosing is not advisable. I would rather advise you to conduct trials before going onto the site and conducting these pourings instead of redosing. Redosing is not advisable.
Okay, sir. Many more times, sir, I have to reject concrete. I have to show segregation or sticky metal or like that lose its plasticity. So I will reject it directly.
Okay. I mean, yeah, depends on
Situation.
yeah, depends on the situation. What kind of a slump you're looking for, uh, and what is the
Hello.
kind of, yeah, what is the kind of pumping time that you're looking at? What is the duration of the pumping and the distance that you're looking to pump it to? So all of that matters. So stickiness is a relative term, as in you're talking about the viscosity of the mix. So yeah, of course, higher viscosity concretes are not useful for us in general terms,
Okay.
in general concreting terms. But again, if you go to 3D printing mixes, so there you want your mix to have a higher viscosity after it has been placed, because otherwise it will spread and you won't have the nature of the form that you want in your mixes. So it depends on the type of concreting that you're looking for, and the what are the parameters that you want to achieve in your mix. So stickiness is therefore relative.
Sir, what is difference in shrinkage and bulging?
Shrinkage and bulging.
Yes, sir.
So shrinkage in concrete, you're talking about that, right? And
Ah,
swelling.
ah,
Yeah, okay. Shrinkage, if I am understanding you correctly, you want to discuss about shrinkage and swelling in concrete, right?
sir.
Okay. Shrinkage is, we've already discussed. Shrinkage is the
Okay.
reduction in volume, and this is essentially occurring in concrete due to the water coming out of the capillary pores in different
Okay.
ways, and therefore the volume gets reduced, right? So that is shrinkage.
Okay. Okay.
What occurs when swelling? How swelling occurs? When you cure your concrete, you essentially dip your specimens in water, or you directly add water to your concrete structures. This
Okay.
external water goes into these capillary pores and refills them, and therefore the shrinkage that has already occurred in the concrete, that gets compensated by a swelling in the concrete. So
Okay.
it is essential that you cure your concrete for a longer period of time, so that this shrinkage that is occurring in the initial days, the plastic and the autogenation or the chemical shrinkage, that is being compensated from outside by the external source of water. So swelling in concrete is basically the opposite of shrinkage. This external source of water that is being sucked out from sucked from the outside by these capillary pores due to the capillary action, and this water comes and refills the pores and also takes part in the reaction. So curing increases the strength, because sometimes it might so happen that the water that you have already added in the concrete mix is not sufficient for the reactions to occur, and therefore you want to provide an external source of water, right? And curing also swells the concrete a little bit and compensates for the shrinkage that has already occurred. So these are the advantages of curing, and that is how you compare shrinkage and swelling. I hope I answered your question.
Yes, sir. I understand.
Okay.
Like,
Okay. right?
सर कोई ग्रुप है क्या व्हाट्सएप का, उसमें कुछ मतलब सवाल रहेंगे तो पूछने के लिए ना?
ग्रुप तो नहीं है, व्हाट्सएप का तो ग्रुप नहीं है, बट शायद आपके लिए एक फोरम बनाया गया है एनपीटीएल के स्वयं पोर्टल पे. If you have any
हाँ,
doubts, you can always raise your questions over there, and any of the teaching assistants will be happy to help you out. और अगर आपको ऐसे ही मतलब दिस इज वेरी इंटरेस्टिंग फॉर मी बिकॉज यू हैव अ लार्ज साइट एक्सपीरियंस, और इफ यू आपको ऐसे अगर डिस्कस करना है देन वी हैव दिस वीकली सेशंस ऑफ 2 hours, एंड मैं जनरली
ओके,
चाहता हूँ कि लास्ट 30 minutes वी कैन हैव दिस डिस्कशंस, सो यू कैन
यस
अटेंड दिस सेशंस एंड यू कैन रेज द
यस
डाउट्स
सर,
ओवर
कभी
देयर.
कभी मुझे काम से फुर्सत नहीं मिलती, मुझे भी मतलब स्टडी करना, और मुझे भी कंक्रीट टेक्नोलॉजी बनना ही है। मैं बहुत सारा लास्ट ईयर आई हैव टू एक्सपीरियंस इन मोर देन 5 years सर एज अ क्वालिटी
ओके.
इंजीनियर।
ओके.
मैं भी कर रहा हूँ सर। कभी
जी
कभी
जी.
मतलब ये होता है। हाँ, तो इसलिए मिल जाता था व्हाट्सएप नंबर या कुछ तो
व्हाट्सएप
मतलब
ग्रुप एक्चुअली ऐसे कुछ है तो नहीं, बट
हाँ,
आप वहां पे फोरम पे डाल सकते हैं स्वयं पोर्टल पे.
ना हाँ, तो स्टडी करके ही डालूंगा मैं भी सर, ऐसे नहीं हवा में डालूंगा।
नहीं कोई
शायद
दिक्कत
मोर
नहीं है
देन
ऐसा. हाँ, ऐसा कुछ नहीं है, आपको जो भी डाउट होता है आप डायरेक्टली उसमें पूछ सकते हैं, एंड कोई
हाँ
टीए आपको हेल्प कर देगा वहां पर.
मोर देन सर, कभी मैं भी एक्सपेरिमेंट करता हूँ सर। अभी मतलब साइट पे इतना बहुत कुछ मिल जाता है सीखने को, अभी कभी कभी क्यूब को स्ट्रेंथ ही नहीं आता है।
जी जी.
मतलब उस टाइम हाँ,
हाँ.
क्या है, हाँ तो फिर मुश्किल से तो फिर रिटेस्ट करना पड़ता है अगेन, ट्रायल एंड एरर बेसिस मेथड लेना पड़ता है, कुछ
जी
एडमिक्सर
जी.
चेंज हुआ तो वो बात। हाँ,
जी बिल्कुल.
मेरा हाँ मेरा मतलब अगेन एंड अगेन रिपीट है कर सकते हो उसको, तो वही
हाँ.
मेरे को भी पूछना था मैं, तो उसके लिए क्या कुछ है क्या ऑलरेडी, मतलब कभी ट्यूब को स्ट्रेन नहीं आया तो अपन उसके लिए क्या सकते हैं। अभी मैं तो क्या कहता है, नंबर ऑफ डेज अभी तक मैं शायद 256 डे तक गया हूँ।
ओके.
कभी कभी मैं टू हाँ टू
हाँ
फिफ्टी
हाँ.
सिक्सटी मैंने ये प्रोजेक्ट में मैंने जो स्टार्टिंग में क्यूब रखा था ना, तो
जी.
उसको आई थिंक मैं 2 साल तक लेके जाने वाला हूँ, 365 डेज तक लेके जाने वाला हूँ एक क्यूब को। ये
अच्छा.
मेरा टारगेट है।
अच्छा.
एडवांस पोटेंशियल है हाँ। तो उसको M40 का है, तो 1 साल के बाद कितना स्ट्रेंथ आता है उसको देखना है मुझे भी।
ठीक है. बढ़िया है, आप ऐसे
हाँ,
एक्सपेरिमेंट्स करते रहिए और हमें बताते रहिए.
हाँ सर, बिल्कुल। सर आप लिंक्डइन पे है क्या सर?
हाँ, मैं हूँ लिंक्डइन पे.
ठीक है, मैं देखता हूँ सर, सर्च करता हूँ मैं, नहीं
ठीक है.
तो अब मिल जाएगा।
आपका अगर स्ट्रेंथ नहीं आता है तो आपने ये कंक्रीट टेक्नोलॉजी कोर्स लेके आपने अगर देखा होगा प्रीवियस लेक्चर्स, तो आपको क्या लगता है स्ट्रेंथ क्यों नहीं आता है, मतलब आर यू टॉकिंग अबाउट अर्ली स्ट्रेंथ और लेटर एज स्ट्रेंथ, मतलब 20 डेज के बाद की इनिशियल डेज की स्ट्रेंथ की बात करें आप, 1 डे, 3 डे, 7 डे.
1 डे वो 7 डेज भी बोल रहा हूँ और 28 डेज का भी बोल रहा हूँ, 28 डेज की भी बात भी नहीं आता है, मैक्सिमम 50% तो आ जाता है, लेकिन
हाँ.
50% के बाद गेन नहीं होता है, तो कभी कभी ह्यूमन एरर भी है, लेकिन ह्यूमन एरर तो एक दो सेट के लिए रहता है, मैं तो 3 4 सेट देखता हूँ ना।
हाँ
मैं
जी. हाँ जी.
मोस्टली 12 भर देता हूँ।
हाँ.
मोस्टली मेरा गाड़ी आता है तो हर एक गाड़ी में 3 क्यूब 1 सैंपल तो रहता है, ह्यूमन ईरर तो नहीं बोलते। लेकिन कभी कभी क्या होता है सर, सिल्ट कंटेंट ही मैं तो मोस्टली बोल दूंगा कि सिल्ट कंटेंट और सॉइल और वेरी फाइन पार्टिकल्स की वजह से, या तो फिर सिमेटिएशस प्लांट पे सिमेटियस मटेरियल कम कर दिए रहते होंगे,
जी जी जी.
तो या फ्लाई एज बढ़ा के भेजते रहेंगे, मतलब 380 अपना मेरा जो है कंटेंट M30 के लिए 380 है,
जी जी.
थ्री थ्री प्लस 60 है, तो वो क्या करते रहेंगे, 100 फ्लाई डालते रहेंगे और 320 सिमेट्रीज डाल देते रहेंगे, और क्या है, फर्जी बेडशीट तो दे सकते हो। तो हाँ,
एक्चुअली
क्योंकि मैंने
यही है कि
ऑलरेडी
क्वालिटी कंट्रोल इतना खराब है, और
हाँ,
इसकी वजह से ही मतलब हमारे कंट्री में आपके जैसे क्वालिटी कंट्रोल इंजीनियर्स की जरूरत है, क्योंकि इतना मतलब कुछ बहुत ही गलत तरीके से साइट पे हैंडल किया जाता है चीजें. जो कि कोड में ना ही प्रोविजन है, ना ही कोई साइंटिस्ट का कोई या फिर कोई कंसल्टेंट का रेफरल है, कुछ नहीं है। तो लोग बहुत ही मोनोपोली चलता रहता है, ऐसी चीजें होती हैं, और फॉल्स बैच शीट्स और फॉल्स मिक्स डिजाइन शीट्स ये सब चलती रहती है। तो बहुत देयर इज अ लार्ज इशू ऑफ दिस क्वालिटी कंट्रोल इन द कंट्री, एंड we want
सर मैं
people like you to be the pioneer of quality control, at least in this industry. Yeah.
इसके लिए तो मैं आया हूँ सर। क्वालिटी कंट्रोल में बहुत मतलब पिछले 7 ईयर्स में बहुत कुछ सीखा हूँ। मैं लास्ट प्रीवियस ईयर अभी कल्पतरु में हूँ। लास्ट प्रीवियस ईयर एनसीसी में था,
जी
तो
जी, आप
एनसीसी में
प्लीज
नहीं था।
किसी का भी नाम मत लीजिए, इट्स अ रिकॉर्डेड लेक्चर, तो आप किसी का नाम मत लीजिए, इट्स ऑल राइट, ठीक है। जी
वो पर्सनली बोलेंगे सर, और मुझे आपसे बहुत कुछ सीखना है। मैं
जी जी,
साइड का
बिल्कुल।
दोस्त।
आप हाँ, आप मत मेरे को मेल कर सकते हैं, एंड आई विल बी हैप्पी टू हेल्प। जो भी मेरे को
हाँ
जितना
सर।
भी पता होगा मैं बता दूंगा।
हाँ सर, मुझे भी बताइए। मेरे को मुझे मुझे लीड करना है। मुझे कंक्रीट टेक्नोलॉजिस्ट ये बनना है। अभी मैं तो पीजीडीएम के लिए एडमिशन भी लिया हूँ सर।
जी जी, ठीक है, ओके, थैंक यू।
थैंक यू सर। सर आपका नाम, शुभ नाम?
आशीर्वाद, आशीर्वाद
आशीर्वाद।
सतपति।
हाँ, मैं आपको लिंक्डइन पे रिक्वेस्ट भेज देता हूँ सर, प्लीज एक्सेप्टेड इट।
ठीक,
और मुझे गाइड कीजिए सर से। कुछ
बिल्कुल
रॉन्ग
बिल्कुल।
नॉलेज भी है। हाँ
आप
सर।
आप ये लेक्चर्स अटेंड करिएगा, एंड अगर आपको टाइम मिलता है, एंड हम डिस्कस करेंगे आपको जब
हाँ
भी
सर,
टाइम
डेली करूंगा ना। मैं क्या कर रहा था सर, आई आई फॉरगेट इट, बट मेरा रूल है कि मैं जापानीज टेक्निक यूज करता हूँ। आपको आई यू हैव टू नॉट बिलीव ऑन मी सर, लेकिन मैं पेपर पे लिख के रखता हूँ। मुझे डेली मतलब मैं लास्ट प्रीवियस वीक से सोच रहा हूँ कि मेरे को लेक्चर अटेंड करना है, बट दे हैव नॉट अटेंड फॉर
मिलता। ओके, इट्स ओके।
वर्क फॉर वर्किंग, क्योंकि 2 to 3 डेज में मेरा 5 बिल्डिंग्स और 2 to 3 डेज में कंक्रीट इतना चलता है कि अब वो मतलब मैंने कल ही 350 क्यूबिक मीटर किया है। एक ही फुटिंग का 350 का।
अच्छा अच्छा,
तो हाँ, वेरी इंटरेस्टिंग।
नाइस।
एक ही फुटिंग था तो वो, हाँ। तो मतलब इतना कंक्रीटिंग ही चल रहा है कि अभी तो मतलब रेनी सीजन नहीं है ना, तो रेनी सीजन में फुल स्टॉप हो जाता है। तो अभी इतना धड़ाधड़ चल रहा है कि मतलब बहुत काम चल रहा है।
ठीक है।
आज आज तो छुट्टी है। कल पोर खत्म हुआ। अभी वापस ऑर्डर डाला। अभी कल वापस पोर चालू हो जाएगा। कल कम है, वो 150 तक जाएगा। एक स्लैब है और बस बाकी कुछ कॉलम रीजन है, वो तो बस बाकी कुछ नहीं है। और मतलब दे हैव वेरी रिकमेंडेड मोर essentials कंपनी प्रोवाइडेड फॉर कंक्रीट लाइक दैट। अभी आप नाम नहीं लूंगा मैं। और वो बहुत खतरनाक होते थे।
ठीक है, ठीक है,
हाँ।
ऑलराइट।
हाँ सर, थैंक यू। चलो सर,
ओके,
थैंक यू सर, हैव अ नाइस डे।
ओके,
थैंक
यू
यू सर।
टू। थैंक यू। All right, if you have any doubts, then you can ask them and we can discuss.
Hello, sir.
Hi, Tobias.
Yes, last time you promised us that
Yeah,
we will
actually,
continue.
there was a technical issue on my side, so I could not take up the online lecture the last week. So I have already recorded the video. So I talked with the NPTEL officials what to do in this case, and they told that you can record it on your own and then you can upload it. So I'll be uploading this to YouTube anyway, and so I have not yet uploaded, and you'll get it in a day or two, and you'll be informed. So I've already recorded I mean that last week's session. I've completed that, and I'll upload it soon, and you'll get the recorded video of that. So you can watch that, and if you have any doubts still, then we can discuss. Or if you have any doubts right now, also we have some time. I guess we have 10 minutes, and we can discuss.
Okay, sir. I think we will discuss it after maybe I watch the
Okay, all
videos.
right. Yeah, I'll upload it in a day or two, and you can watch it, and then we can discuss it in the next session. Right?
Okay, thank you.
Okay. All right, if you don't have any more doubts, then let's close the session for today, and we'll meet again on the next Monday from 6 to 8 p.m. Thank you.